Hello everyone. So I like to go clubbing from time to time, usually electronic dance music, and I saw those lighting shoes a while ago. I thought, those are pretty cool. Obviously different brands. They're pretty cheap. You can get them for about 50 bucks, which is almost too cheap actually. That's why they go bad in multiple ways. As you can see, all the LEDs are the same color, except if actually they're starting going to go bad, and then there'll be different colors, but not by design. There's a little button on the side where you can change the pattern, and the battery inside is usually only good for about 4 hours. So I've actually hacked mine, put a much bigger LiPo on them inside the shoe, so I can get about 12 hours. And that was my first little project. I'll give a link on that since I already have a page. But anyway, if you like to tinker, usually you go shop around and flea markets and things like that. And I found this LED strip. 3 colors are LEDs, and you can see here RGB with ground, and you have this little controller here which takes infrared and will output different colors, but all the LEDs are the same because they're not addressable. That's why it's 10 bucks for the whole strip, which is incredibly cheap. Now, okay, I have this strip now. What can I do with it? And well, I can put them on a nice silver shirt. So I have this other demo here. Let me turn this one off on a different pack here and turn this one on. This one a bit more fancy. I'll start with the controller I made. So I'm using those batteries, 18650, same ones that are in my Tesla car. And this is actually a LiPo tester per cell. So I've actually added per battery wires to go to that tester, so it will show me how each cell is doing, and that way if I have one battery getting too low, I can start getting warnings, which are the beeps you heard. Those are usually supposed to be protected, where if they get too low, you can recharge them. I suppose they won't go flat and die, but it's iffy. Some of them do not recover very well, so it's better to not take them below 3 volts, and that will ensure that this doesn't happen. So from here I have a few boards. I'll start with this one. This I got from Amazon, also reasonably cheap, one of the many drop power boards. This one is actually used to change the voltage, and it will show me obviously how many amps are going out. The reason for that, and I'll show you the shirt here, is same thing. It's the same concept of LEDs in 3 colors. You can see the wires in between, RGB and ground. If I were to limit the current to a given value as the color patterns change, then the current wouldn't match the color pattern. Let's say just blue would be getting way too many amps, and then white would be getting not enough. So that's why you can see the amp number changing here. The reason why I have this board is that the LEDs actually ended up being too bright and were blinding people in the clubs, and I like to be shiny and all, but I don't want to be obnoxious. So on the LEDs, you can control the intensity by changing the voltage. They're actually meant to be for 12 volts, but if I take the voltage down, you can see right now I'm using 1 amp or more depending on what's being lit. Then they end up being too bright. Also, the batteries will not last as long. Those batteries are about 3 amp hours, give or take. So that would only give me about 4 hours of runtime. So I can take the voltage back down to about 8 volts, and now you can see I'm using like 1/3 or 1/5 of an amp. So that will get me running for more than about 24 hours. So this is how everything started. Now you can see obviously those LEDs are shining and changing patterns. That's using an LED controller, which is hidden down there on the shirt. Let me make some room here. So this little guy right there is the controller. It takes input 12 volts, or 8 in this case, output RGB, and the connection between the LEDs tend to break and not be very reliable, so I have wires in a few places to duplicate the connection in case, let's say this one breaks. If one color is missing, it will be fed from the other side to give redundancy in basically what is a bus. It looks a bit ghetto, but it works. So all those LEDs again are supposed to be the same color. In real life they're not exactly, and the reason is again, one of the connections here and there, despite my redundant wiring, some of the connections are actually broken. So it gives me a bit of extra color patterns, but that's not by design. The board here comes with a pretty fancy remote. I'll show you the remote right here. Plenty of colors. So if I want red, green, and blue, and you can pick all those other colors, and then some auto mode where I'll just flash different colors. I can do fading, which is a bit actually more smooth transitions, and then I can go quick, and I can go on slow. It will slow them down. So actually if I go in auto mode and let's see, more quick, you get some pretty crazy stuff like that. So that's nice, you know, it worked pretty well. But again, all the LEDs are the same. You cannot have patterns going up and down them. It's just the same thing on all the LEDs. Modular, the ones that are a little bit broken. But that was the start. Okay, so in my previous demo I was showing this LED strip with the controller here. You can use the remote to turn on and off, change colors, but all the LEDs are the same color. This one uses 12 volts, so I have like that 12 volt power supply over there, well 12 volts-ish. You can just take the current down by taking the voltage down. There's actually a lower brightness button, but it only works on full colors. Once you go into auto modes or fade modes like these, they go full current. You can see it's very bright, and there's nothing you can do to take the current down except taking the voltage down. So that's what I've been doing. Anyway, so those are for those boards. Now the cool board I found is this little guy, which is, instead of using a remote control, is actually Wi-Fi. It's an ESP8266 inside, and thanks to that I can actually use my cell phone to again talk to the strip and change colors, but it will be the same color for all the LEDs, which is not what I want. So that's where the Neopixels come in. Neopixel rings come in different ways, or in this case strips. The way they work is you have 3 wires. I'm trying to zoom in. You have 5 volts, then you have DN, data in, and then ground. So this is wired in a different order than the servo cables I'm using. So I'm rewiring this servo cable to have the signal in the middle and ground and 5 volts. This goes to a power converter board here, which is just taking the same voltage and signal and multiplying it. This is actually all servo stuff from my RC remote control planes. And this 5 volts goes to this little capacitor as recommended by Adafruit. That's just to prevent current onrush from damaging the pixel. In there I have a resistor for the data line, and it's going to an Uno. So the Uno is really just sending a data signal, and the 5 volt is coming from that power supply over there. You can see right now my strip is taking 2.1 amps, which will be way too much for an Arduino board, which is why I have that the power supply. Now it's actually not using all the LEDs, which is why it went down to 0.9 amps. Okay. So that's how the system works. The way you connect it, I'm going to show you here. Each strip has a DIN and DOUT, so each pixel is connected to the next one. I thought you could just connect in the middle, like I would do here, and nothing happens. So what's going on is that the DIN that I'm connecting to is also connected to the DOUT of the previous LED, and that DOUT actually sucks the signal out, which prevents it from working. So you can only connect to the last LED, or I should say the first one in the strip. And I'm going to try to do this here. Okay, so that shows you the connections. Red, 5 volts, white is the data line, and black is the ground line. And I'm using those pins to connect. You can see better if I turn off, because of course the LEDs tend to be a little bit too bright for the camera. So that shows you how it works. If you have a strip not working, again, you cannot just try connecting to the pixels in the middle, because each pixel before that is going to take your data signal and suck it down to ground, preventing it from working. So you can only connect to the last LED, and if it doesn't work, you have to cut it off right here and connect to the next one. So now the interesting thing is, how do you actually do the controller board, and which kind of software you can write to talk to it, and I will talk about that. Alright, so for my project, I want to drive that strip here. I'll have a couple of strips going down either my shirt or the side of my pants, and the idea is to obviously have the LEDs be controllable separately to do some nice effects. The Arduino Uno board is obviously way too big for this. It will work, but it's not exactly, actually it won't work, and I'll explain why. But for just lighting up the strip, it will do the job, but it's way too big. That's the chip in it. It's a 328p, the old venerable chip. It's about yay big. And the newer versions of the same chip look like this, like the one here. Same chip, just different form factor. So that's actually an Arduino Nano V3, which is functionally the same board. But I had bought a long time ago that Arduino, which is basically a backpack for the chip. So you take the chip and you actually solder on that little board on the pins, and then the actual pins from the chip go into your breadboard, although in this case I'm not using the breadboard, it's just to hold the chip for this video. And then I soldered two I/O, one for the LED strip, and the other one will take the infrared signal going to a different rows of pins. Just for comparison, here we have a 32-bit AVR chip. That's I forget what this one is called, but I think it's a Nano. Yeah, the name escapes me. But it's Teensy version 3.1. That's actually a very nice chip, much more power, better I/O, and it's probably actually the most capable chip on here. Anyway, the first problem I had when I put this chip is I probably stole it from another project and put in a bare chip I bought, and the bare Arduino chips don't actually work. They don't have a bootloader or anything, so I had to burn a bootloader. The way you do that is you use an ISP programmer like this one, and this is actually meant to connect to the ISP plug that you have like here, this plug right here, ISP header, one right there. Obviously this bare chip doesn't have it, so I looked online to see what the pins were. I mapped them out, and then I basically just put them on a breadboard to connect to the correct pins of the Arduino, and that's how I was able to use the ICSP programmer to not only flash something but also put a bootloader, so now it would actually boot and take serial to allow me to flash it. So again, there's no FTDI or anything on this chip, it's just the bare RxTX pins, and the way you program in that case, you use one of those little guys, which is a separate board that has an FTDI equivalent on it and puts out RxTX. This one is really nice because you can actually invert the pins, and you can do 3.3 volts or 5 volts with those little switches. I wish I could buy more of these, but apparently they don't exist anymore. There's a toothpick on the side, and there's actually also a toothpick here, and this is how I make sure that I don't plug it in the wrong direction, because that would probably be pretty bad. So right now plugging in just gives power to the chip, but that's also how I would program it, and once it gets powered it will boot and display the LED. So let me just plug it in to show, there we go, and then it's coming on. So that's my chip. That's the easiest and smallest way to do it. Sadly, as I found out later, it will talk to the strip just fine, but it's not able to do infrared and programming this, talking to this strip at the same time. The problem is, to talk to those LEDs, you have to send a signal at 800 kilohertz, and that signal needs to be perfectly timed, and the only way you can do it is by stopping interrupts, which in turn prevent the infrared driver from working. So it turns out I spent quite a bit of time trying to make it work, but it would not work with infrared and talking to the strip at the same time. You can send something, but then you cannot update, because when you update, then infrared stops working. Alright, so now I have that 328p Arduino running my code, which sends different demo illuminations on that LED strip. And the idea is I'm supposed to be able to change what is being displayed with the infrared remote I have. So I added that little infrared reader here, which is just a signal pin, power and ground. And then by pushing buttons like here, red, it is supposed to make the strip go red. Obviously it's not going on here, not working. So let's look at the serial monitor here. While I'm pushing the button red, you're going to see FF or other garbage data. And effectively what's going on is the interrupt handler for this IR needs to run at an exact time. Otherwise, it's not sampling the infrared coming in from the remote quickly enough, and then it's getting the wrong signals, maybe dropping bits and reading something else and giving me other data in the end. And what's going on is the Neopixel strip here has a similar timing issue where it needs precise 800 kilohertz timing for those LEDs to get the right color. Otherwise, they will just display a different color than what you're trying to send. So here I'm using the fast LED code, but you can use the Adafruit library too. And they both have the same issue. Well, it's not an issue. They have to be running a CLI here. Whoops. And the CLI will actually tell interrupts to stop. So once this runs, it has full control on timing for the LEDs. So they give you the correct color, but then the infrared is not running quickly enough and it's returning garbage like this. So, okay, well, I guess what we can always try to do is we can disable that CLI and see what happens. Let me save that file. Recompile and re-upload the code. Alright, almost pushed. And we're done. Alright, so I'm going to stay on the screen for now. I'm going to push the remote off screen. I'm going to push red. And now, look at this. It is getting the red. I'm going to push green. Oh, okay, it's getting green too. So now my interrupt handler that's receiving the AVR command is actually working properly because it's not being interrupted anymore. Perfect. Except now the LEDs aren't doing what they're supposed to do anymore. What you're seeing here is all supposed to be green and you're seeing random other colors in the middle. This happens when the interrupt handler for the infrared is running. So you basically lose one no matter what. If the infrared is working, then the LEDs aren't working properly, or the other way around. I'm going to send some blue. So you can see the command is going through, right? The blue is being sent. But as it's resending that blue, some of the pixels are getting garbage colors instead. There is one way around it. If you're willing to live with just sending the blue and then not doing anything, not updating the LEDs, and then the infrared works, so you do LED update or IR reading, then it would work. But it wouldn't do both at the same time. The problem is I have demos like this one. Let me push this button, which are constantly updating the LEDs. It's basically a flame effect. So the LEDs just change colors all the time, which would mean that the infrared would never work because the LEDs are always busy changing. And basically it comes down to there's no good solution. This chip, the 328P, is just not powerful enough to do both in real time. Some people have taken a solution where they take two chips. They take one for the infrared, one for the LED driving, and then both chips talk to one another. So the first one reads the infrared command, buffers it, and sends it to the second chip, which is busy sending infrared commands. And the talking between doesn't have to be real time. That is one solution, but of course I prefer to have one chip. And the only way around that is to take a more powerful chip, which is what this one is, Teensy. Teensy is actually a 32-bit AVR, sorry, not AVR, an ARM chip, which can run quickly enough to run both at the same time, and I will show this next. Alright, so now let's look at the same code again. I haven't changed anything, using the Teensy 3.1 32-bit AVR chip, and that chip is just so much faster than your basic Arduino. So let me try to send blue, green, red, and then while I'll go into an auto mode where the LEDs are constantly changing. It's a little bit hard to see on video, but yeah, you can see them transitioning. That means that the chip is spending its entire time updating the LEDs. So it has to send that exact timing. However, if I go push a remote key, it still is able to take it just in time. And I can look here on the screen. We send red, so you can see the red is going through. So what's going on? Well, the fast LED code is actually much better than the Adafruit code and supports architectures better. If you look at the highlighted line here, in the middle of updating the LEDs between each pixel, it's actually able to send the beginning of the wave, and then the chip is so fast that it can actually stop, re-enable the interrupts, SEI, then it will wait for a number of microseconds during which the interrupts can fire, and this is where the infrared interrupt that was waiting gets to run, and that's why it's receiving the code. And then, because that interrupt runs quickly enough, it's able to run within that delay time, and when the interrupts are cleared again, CLI meaning disabled, then the infrared cannot run anymore, but it was able to gather enough data just in between that pixel update time. So that's how it's able to do both at the same time. By just switching quickly enough between two time critical tasks, it's able to take it and do the right thing. So I can send more codes, and you don't see all the LEDs updating, but you can see that it's receiving all my commands and getting the LEDs busy, changing all the time. So that is the Teensy. That's how you actually benefit from having a faster CPU. In my case, I try to get the cheapest one because, well, you know, I like to save. I don't like to spend more resources than I need to for a task, but it's actually, in this case, a task that requires a fast enough CPU like this one, or two different ones talking to one another. I hope this was helpful. Alright, my last update, I showed how the Teensy was a capable enough CPU to run a Neopixel strip and at the same time run interrupts to read from my infrared remote. Now, the thing is, it's actually a very capable chip with a lot of I/O, and I felt a bit stupid wasting that chip on just two pins, one for the infrared and one for the Neopixel, when actually it's capable of running 8 Neopixels at the same time, 8 strips, which I didn't need for my project here. So I had some ESP8266 chips, and that's one of them here. Those are even cheaper. They're about $10 a piece, and they have Wi-Fi built in. They have a lot less I/O, which actually in this case works out because I only need, again, 2 pins. So I thought, oh, okay, maybe I can make it work. And let's have a look here. That's the infrared. There we go, turning it blue, green. So basically that chip is able to run the interrupts for that infrared reader and send at the same time real-time updates. I'll use a better demo like that updates all the time, like this one. While it's sending those constant updates, it's still able to read from the remote, and there's no glitches. It doesn't work well with the fast LED support while doing infrared because the interrupts are a little bit too long, but it actually has an audio I2S support, which has been abused to run the Neopixel that you're seeing right here. Someone wrote that driver, and that's what I'm running right now. So it's actually able to do interrupts and run a Neopixel with no problems, no glitching. Now we have, of course, the bigger chip from the ESP8266, which is the new ESP32. That's a bigger devel board, but the chip itself is this one right here. It's very capable. It has 8 channels to do any kind of square or wave signal that you need. So in this case, it's able to run that Neopixel just fine without any work from the CPU. It's just being done by its RMT subsystem, and the CPU is able to run interrupts and do infrared at the same time, plus plenty of other things. So that's another option to be running Neopixels. Of course, that board is very big, but you have much smaller chips. So that's the ESP32 and the ESP8266. They're all running different codes. So this one's running, again, an RMT driver. This one's running an I2S driver. It's I2C, but for audio, it's called I2S. Whereas this one was running bit banging, and it was just fast enough to do it. So there you go. This is how you can do Neopixels plus do infrared at the same time.